Most elevator motors are considered intermittent duty. Intermittent duty refers to motors that are not intended for continuous operation. Elevator motors typically operate for short periods of time, with pauses in between. This type of duty allows the motor to cool down between operations. You must size your overcurrent protection device, or OCPD, according to the peak starting current. The OCPD is designed to trip when the current exceeds a certain value. In this instance, the peak starting current is 278 amps. The OCPD must be rated for at least this value to prevent damage to the motor. The running current of 121 amps is not relevant for sizing the OCPD, as the OCPD is only concerned with preventing overcurrents. It is important to note that the peak starting current can be much higher than the running current. This is because when the motor starts, it must overcome the inertia of the load. Once the motor is up to speed, the current will drop to the running current. Choosing the correct OCPD is essential for protecting the motor from damage. If the OCPD is too small, it may trip prematurely, causing the motor to stop. If the OCPD is too large, it may not trip in time to prevent damage to the motor in the event of an overcurrent. Understanding intermittent duty is crucial for selecting the correct motor and protective devices. Motors designed for intermittent duty are built to withstand the thermal stresses of frequent starts and stops, but they cannot dissipate heat as effectively as motors designed for continuous operation. This distinction affects the motor's insulation, winding design, and overall construction. Sizing the OCPD correctly is not just about preventing nuisance tripping, it's about ensuring the safety and longevity of the motor and the electrical system. An undersized OCPD can lead to unnecessary downtime, while an oversized OCPD can allow a damaging overcurrent to persist, potentially causing a fire or equipment failure. When selecting an OCPD, consider the motor's nameplate data, including the full load amps FLA, service factor, and temperature rise. Consult the National Electrical Code, or NEC, for specific requirements related to motor protection. The NEC provides tables and guidelines for sizing OCPDs based on motor type, voltage, and application. For example, NEC Table 430.52 provides guidance on maximum OCPD sizes for different types of motors. In addition to the OCPDs, consider using a motor starter with overload protection. Overload relays are designed to protect the motor from sustained overcurrents that are below the OCPD trip threshold. These relays typically have adjustable trip settings to match the motor's FLA. The overload relay will trip if the motor draws excessive current for an extended period, preventing overheating and potential damage. When dealing with elevator motors, it is important to consider the specific requirements of the elevator system. Elevator motors often experience high starting torques and frequent reversals, which can place additional stress on the motor and electrical system. Consult with elevator manufacturers and qualified electricians to ensure that the motor and protective devices are properly sized and installed. The starting current of a motor is typically several times higher than its running current. This inrush of current occurs because the motor's rotor is initially at rest and requires a large amount of current to overcome its inertia and begin rotating. The magnitude and duration of the starting current depend on factors such as the motor's design, load inertia, and applied voltage. Various methods can be used to reduce the starting current of a motor, such as reduced voltage starters, part winding starters, and variable frequency drives, or VFDs. Reduced voltage starters, such as auto transformers and reactors, reduce the voltage applied to the motor during startup, thereby reducing the starting current. Part winding starters connect only a portion of the motor's windings during startup, gradually increasing the current as the motor accelerates. VFD provide the most sophisticated method of motor control, allowing for precise adjustment of the motor's speed and torque. VFD can significantly reduce the starting current by gradually increasing the motor's speed from zero. The choice of starting method depends on the application's requirements, including the motor size, load characteristics, and cost considerations. For elevator motors, VFD are often used to provide smooth acceleration and deceleration, improve energy efficiency, and reduce wear and tear on the mechanical system. In addition to the OCPD and overload relay, other protective devices may be required to protect the motor and electrical system. These devices include surge suppressors, which protect against voltage transients caused by lightning or switching events, ground fault protection, which detects and interrupts ground faults, and phase monitors, which protect against phase loss or imbalance. The NEC provides specific requirements for these protective devices based on the application and voltage level. Proper grounding is also essential for motor protection. A properly grounded system provides a low impedance path for fault currents, allowing protective devices to quickly clear the fault. Grounding electrodes, grounding conductors, and bonding jumpers should be installed in accordance with the NEC to ensure a safe and reliable electrical system. Regular maintenance and testing are crucial for ensuring the continued effectiveness of motor protection devices. OCPDs should be periodically tested to verify their trip characteristics. Overload relays should be inspected for proper operation and calibrated as needed. Grounding systems should be inspected for corrosion and loose connections. By implementing a comprehensive maintenance program, you can identify and address potential problems before they lead to equipment failure or safety hazards. When working with electrical equipment, always follow safe work practices. To energize and lock out equipment before performing any maintenance or repairs. Use appropriate personal protective equipment, or PPE, such as gloves, safety glasses, and insulated tools. Consult with qualified electricians and engineers to ensure that electrical work is performed safely and in accordance with applicable codes and standards. In summary, selecting and installing the proper OCPD for an elevator motor requires careful consideration of several factors, including the motor's peak starting current, duty cycle, and application requirements. Consulting the NEC and working with qualified professionals are essential for ensuring a safe and reliable electrical system. Always prioritize safety and follow established procedures when working with electrical equipment. The peak starting current of a motor is the maximum instantaneous current drawn by the motor during the starting period. This current can be significantly higher than the motor's full load current, sometimes reaching 6 to 8 times the FLA. The duration of the peak starting current is typically very short, lasting only a fraction of a second. However, this high current can cause voltage dips in the electrical system and can stress electrical components such as conductors, transformers, and switchgear. The OCPD must be able to withstand the peak starting current without tripping, while still providing protection against overcurrents. Time delay fuses and inverse time circuit breakers are commonly used as OCPDs for motors because they have a built-in time delay that allows them to ride through the peak starting current. The time delay must be long enough to prevent nuisance tripping, but short enough to provide adequate protection against overcurrents. The NEC specifies the maximum allowable time delay for OCPDs based on the motor's type and application. In addition to the OCPD, the motor's conductors must also be sized to carry the peak starting current. The NEC provides guidelines for conductor sizing based on the motor's FLA and the type of insulation used. The conductors must be large enough to prevent overheating and voltage drop during the starting period. Voltage drop can be a significant concern when starting large motors, especially in long cable runs. Excessive voltage drop can cause the motor to start slowly or fail to start altogether. Voltage drop calculations should be performed to ensure that the voltage at the motor terminals remains within acceptable limits during startup. The impedance of the electrical system, including transformers, conductors, and switchgear, affects the voltage drop during motor starting. A low impedance system will minimize voltage drop, while a high impedance system will exacerbate it. When designing an electrical system for motor starting, it is important to minimize the system impedance as much as possible. This can be achieved by using larger conductors, shorter cable runs, and transformers with low impedance. In some cases, it may be necessary to use a dedicated transformer to supply power to a large motor to minimize voltage drop. The type of load connected to the motor also affects the starting current. Loads with high inertia, such as fans and pumps, require more torque to start and accelerate than loads with low inertia. The motor's starting torque must be sufficient to overcome the load's inertia and accelerate it to its operating speed. If the motor's starting torque is insufficient, it may stall or take an excessively long time to start. The motor's nameplate data provides information about its starting torque capabilities. The nameplate typically specifies the motor's locked rotor torque, pull-up torque, and breakdown torque. The locked rotor torque is the torque produced by the motor at zero speed, the pull-up torque is the minimum torque produced during acceleration, and the breakdown torque is the maximum torque the motor can produce without stalling. The motor's starting torque capabilities must be matched to the load's requirements to ensure reliable starting. In some cases, it may be necessary to use a motor with a higher starting torque or a reduced voltage starter to improve starting performance. The ambient temperature also affects the motor's performance. High ambient temperatures can reduce the motor's insulation life and increase its operating temperature. Motors operating in high ambient temperatures should be derated to prevent overheating. The motor's nameplate data typically specifies the maximum allowable ambient temperature. If the ambient temperature exceeds this limit, the motor's horsepower rating should be reduced accordingly. The motor's cooling system must also be adequate to dissipate heat effectively. Motors are typically cooled by air or liquid. Air-cooled motors rely on fans to circulate air around the motor windings. Liquid-cooled motors use a circulating liquid, such as water or oil, to remove heat from the motor windings. The cooling system must be properly maintained to ensure adequate cooling. Fans should be kept clean and free of obstructions. Liquid cooling systems should be checked for leaks and proper coolant levels. Proper lubrication is also essential for motor life. Motors should be lubricated according to the manufacturer's recommendations. Over-lubrication can cause grease to leak into the motor windings, while under-lubrication can cause bearing failure. The type of lubricant used should be compatible with the motor's bearings and operating conditions. Synthetic lubricants are often used in motors operating at high temperatures or under heavy loads. The motor's enclosure also affects its performance. Enclosures protect the motor from environmental factors such as dust, moisture, and corrosive substances. Enclosures are classified according to their degree of protection. NEMA, or National Electrical Manufacturers Association, standards define the different enclosure types. Open drip-proof, or OP, enclosures provide minimal protection, while totally enclosed fan-cooled, or TEFC, enclosures provide maximum protection. The enclosure type should be selected based on the motor's operating environment. In dusty or wet environments, a TEFC enclosure is recommended. In clean, dry environments, an ODP enclosure may be sufficient. Regular inspections can help identify potential problems early. Motors should be inspected for signs of overheating, vibration, and unusual noise. Bearings should be checked for excessive wear or play. Windings should be inspected for insulation damage. Any problems should be addressed promptly to prevent further damage. Vibration analysis can be used to detect bearing problems and other mechanical issues. Infrared thermography can be used to identify hot spots in the motor windings and connections. These diagnostic techniques can help identify potential problems before they lead to motor failure. Motor testing can be used to assess the motor's overall condition. Insulation resistance tests can be used to detect insulation damage. Winding resistance tests can be used to detect shorted or open windings. Surge tests can be used to detect weak spots in the insulation. These tests can help determine whether a motor needs to be repaired or replaced. Motor repair and rewind services are available to restore damaged motors to their original condition. Motor repair typically involves replacing damaged components such as bearings, windings, and insulation. Motor rewind involves replacing the entire motor winding. Motor repair and rewind services can be a cost-effective alternative to replacing a motor. When selecting a motor repair or rewind service, it is important to choose a reputable company with experienced technicians. The company should use high-quality materials and follow industry best practices. The repaired or rewound motor should be tested to ensure that it meets its original performance specifications. In conclusion, selecting and protecting elevator motors requires a comprehensive understanding of motor characteristics, application requirements, and electrical codes. By following the guidelines outlined in this narration, you can ensure the safe and reliable operation of elevator motors.